Hi. So today we will discuss about the boundary behavior of Riemann band. So we have seen that between any two simply counted domains, which are not the whole complex plane, there is a conformal mapping in a unique way. We can make it unique by fixing some point. So now the question is, can we extend this map to the boundary of that region? So that's what we will consider today. Now, we need a definition. So what we actually mean by extending to the boundary? So what do you mean by a sequence Zn tends to the boundary? Or what do you mean by an arc tend to the boundary? So let me make it rigorous. So a sequence in a region tends to boundary means for every element in omega, you are able to find an epsilon such that after a certain stage, the absolute value of Zn minus Z is greater than or equal to epsilon. That means this sequence will leave the neighborhood of Z. So every Z you are able to find a neighborhood of Z so that the sequence will leave that neighborhood after a certain stage. Similarly, an arc tends to the boundary means for each element in omega, you are able to find a neighborhood and a stage T0 such that the arc will leave the neighborhood of Z. So this should happen for every element in omega. So then we say that the arc tends to the boundary. For example, a simple example, you can consider this disk, unit disk, and you can see that the sequence 1 by n is 1 by n built into the boundary. The epsilon you can take epsilon to be 1 minus mod Z by 2 for any Z in the disk. So that is easy. Now what we do, so we will prove that you start from a topological mapping, a homomorphism of a region omega onto a region omega prime. Then we will see that if Zn tends to the boundary, then its image will also tend to the boundary. Similarly, if Z of t, the arc tends to the boundary of omega, then its image will tend to the boundary of omega prime. So in some sense, the tending to the boundary is preserved under a topological mapping. So for proving this result, what we do, we will characterize the property of tending to the boundary in terms of compact sets. So suppose Zn tends to the boundary of omega, or Z of t, the arc tends to the boundary of omega. So by definition, there exists an epsilon corresponding to each Z belongs to omega, that's an epsilon. It will obviously depend on Z. And a stage n0 or t0 in case of an arc, such that absolute value of Zn minus Z greater than or equal to epsilon, or absolute value of Zt minus Z greater than or equal to epsilon, as n greater than or equal to n0 or t greater than t0. So now what we do, we consider the collection of all such disks centered at each point Z. So it will form an open cover for omega. In fact, we are running over all element in omega, so it will run over. It will give you an open cover for omega. So you start from a compact subset of omega, then this will form an open cover for this compact subset also. And by compactness, you will have a finite subcover. So that means you are getting finitely many elements. We denoted them by Z1, Z2, Zm. And finitely many, corresponding to that, you have epsilon 1, epsilon 2, etc., epsilon m, and n0, n1, n2, etc., with the property that Zn will leave these balls after a certain stage. So that's what we have. So we have this mod Z of I minus Zn greater than or equal to epsilon I for all n greater than or equal to ni, or mod Z of I minus Z of t greater than or equal to epsilon I for all t greater than ti. Now what we do, we choose n0 to be the maximum of these stages, n1 up to nm, and t0 to be the maximum of t1, t2, etc., tn. So that we can apply both these things. So mod Zi minus Zn greater than or equal to epsilon I for all n greater than or equal to n0, and for all I equal to 1 to m. Similarly, for the arc, Zi minus Zt is greater than or equal to epsilon I. But K is a subset of these finite balls, union of these finite balls. So this tells you that Zn leaves each of these balls. That means Zn should leave the compact set K. So if Z belongs to K, mod Z minus Zi should be less than epsilon I for some I. So but Zn will satisfy this inequality. So that means Z of t will be outside K, and Zn will be outside K after these stages. Or in other words, you started from a compact set and we obtained that there actually a stage N0 or T0 in case of an arc, such that after that stage, Z of T or Zn will be outside that compact set. That means it leaves the compact set after a certain stage. This happens when Zn tends to the boundary. Now we see that the converse is also true. You start from the assumption that for every compact set you have this property. That means it leaves after a certain stage, either Zn or arc. We will prove that Zn tends to the boundary. The same for the arc set. So you start from an element in omega and consider epsilon greater than 0 such that the closed ball of radius epsilon is fully contained in omega. So since omega is an open set, such a ball always exists. And you take K to be the closed unit, a closed ball of radius epsilon, and take the closure of that. So that's a compact set. Okay, so it's a closed and bounded set, therefore it's a compact set. And by our assumption, direction N0 such that Zn does not belong to K after n greater than N0, or Zt does not belong to K after t greater than 10. Hence, this will happen after n greater than N0 and t greater than T0. Or in other words, Zn tends to the boundary of omega, or the arc tends to the boundary of omega by definition. Now, this is the characterization we will use to prove that f of z, if Zn tends to the boundary, f of Zn will tend to the boundary. So, assume that Zn tends to the boundary, or Zt tends to the boundary. So, we want to prove that its image also has a property. We start from a compact subset of the omega prime. K prime subset of omega prime be a compact subset. Now, f is a topological mapping, therefore its inverse will be a compact subset of omega. So, K is a compact subset of omega. And by our assumption, Zn or Zt tends to the boundary of omega, therefore it should leave this compact set. So, you have a stage after which Zn outside K and Zt outside K. Therefore, f of Zn will be outside f of K, and so we got the proof. Okay. So we proved that under a topological mapping, this property is preserved. So this is something very important which we will use later. Now we have a couple of definitions. One is of the free boundary arc. So you begin with a simply contour region omega, and suppose that its boundary contains a line segment gamma that lies on the real axis, say an interval a to b. Now, if every point of x, point x of omega has a neighborhood whose intersection with the boundary dou omega of omega is same as the intersection with gamma. That means there are no other boundary points other than the points in gamma in at least one of the neighborhood of x, and this should happen for each element in gamma. Then gamma is called a free boundary arc. For example, if you consider this region as omega, then any sub-interval here will be a free boundary arc, because any point you have a neighborhood such that its boundary of omega intersects with only this line. So it's called a free boundary arc. Now we define what is a one-sided or two-sided boundary arc. Let omega be simply unconnected and gamma will be a free boundary arc. Then by definition, what happens? You have a neighborhood like this, such that this line is the only intersection with the boundary of omega. Okay. Then what happens? Consider the two half disks determined by this diameter. That means this upper disk and the lower disk. Okay. Now, if Z belongs, so you start from an element in omega which is in one of these half disks. Okay. So then what happens? Since omega is open, there is a neighborhood which is fully contained in the half disk. But you know that no boundary points are present in this neighborhood other than the points from gamma. Therefore, the boundary of this disk, the open neighborhood, that will not be part of this. So what happens that that could not be a boundary point of omega. Therefore, that should be a point of omega. So you have more boundary. All the boundary is part of omega. So again, by openness, you can get larger disk, and keep on doing like this. You'll obtain that the whole half disk is part of omega. So the only possibility is that either both these half disks are part of omega, or at least one of them will be part of omega. So this is the possibility. So if both of them are part of omega, we call it a two-sided arc, and if only one of them is part of omega, then we call it a one-sided arc. Now what we are going to do, we are going to extend Riemann map to the boundary of this form. So let us have this result. Suppose that the boundary of a simply conducted region omega contains a line segment gamma as a one-sided free boundary arc. That means only one half disk will be part of omega. Then the function fz, which maps omega onto the unit disk, which is obtained by the Riemann mapping theorem, this can be extended as a function which is analytic and one-to-one on the omega union gamma. I mean, you can extend to the bound to this line segment, which is part of the boundary of omega. And this can be done in a one-to-one way. Also, the image of gamma will be an arc on the unit circle. So this is the way which we do. So you have a line segment like this. So you already have a map F. So this line segment you can map onto some circle, arc on the unit circle. Proof: you start from x0 belongs to gamma, something like this. Then you have a neighborhood around x0 such that exactly one of the half disk is inside omega. Okay, and you can choose this hard disk such that it does not contain the point z0. Z0 has the property that f of z0 equals 0 and f dash z0 greater than 0. So z0 is a part of omega. Therefore, you can very well contain a neighborhood of x0 which does not intersect with z0. So that is possible. Now, therefore, what happens that f will never vanish because z0 is a point which is mapped onto 0 and f is 1, 1. So in this hard disk, f will never vanish. So fz not equal to 0 there. Therefore, log fz has a single valued branch in that hard disk. Now what you do, by previous theorem, you know that if Zt tends to the diameter, f of Zt tends to the unit circle. Because we have seen that under topological mapping, this tending to the boundary is present. So because diameter is the boundary of omega and unit circle is the boundary of f omega, as Z tends to the diameter, mod fz should go to 1. So what happens that log mod fz should go to 0. So by what happens that log fz is not merely defined on the half disk. You have the property that it goes to the limit exists on the diameter. So you can apply the reflection principle. So by reflection principle, you can extend log fz the analytic extension to the whole disk. You can reflect to the whole disk. So log fz is analytic at x0. Therefore, fz is analytic at x0. Now, x0 belongs to gamma was arbitrary. You can do it for any element in gamma. Now, what happens that you will have this kind of situation. x0 here, you have a disk and you extended here fz. Similarly, x1 here, you extended here to the disk. Now, there will be some intersection points. So it will be well defined only if they coincide on the intersection. But this is true because on the upper half disk, they should coincide because f is already well defined on the upper side, one half disk. It is part of omega. So this region, it will be in this intersection, this upper region, it will be equal. So they will be equal. Therefore, by identity theorem, they should be equal everywhere. So it is well defined. So everything is fine. The only thing we have to prove is that this is 1, 1. 1, 1 on the extension is 1, 1. That means it is 1, 1 on gamma. So for that, we will prove that derivative does not vanish on gamma. Suppose f dash x0 is 0. And we consider the power series representation in this way around x0. And you choose k to be the largest integer such that kth derivative at x0 is 0. So obviously k is greater than equal to 0, greater than 1 since f dash x0 is 0. So you have something like this, f dash x0, you can take this z minus x0 over k plus 1 outside. So you can write it as this, a0 plus z minus x0 over k plus 1 into gz, where g of x0 not equal to 0. So in a disk of around the x0, you have gz not equal to 0. By continuity, you will obtain that. Therefore, you have an analytic branch of gz power 1 by k plus 1. Okay, so you can write fz as a0 plus this quantity all power k plus 1. So this quantity, so this has k plus 1 branches because we are taking the k plus 1th root here. So you denote those branches by g1z, g2z, etc., gk plus 1z. Okay. Now notice that, see, recall that if you, the definition of root z, the function root z. So what happens that if you consider two arcs like this meet at x0, gamma 1 and gamma 2 like this with an angle pi between them, then this image under root z, these images of this gamma 1 and gamma 2 will have angle pi by 2. if you are taking the function to be root set. So that's what happening for root set. Similarly, if you are taking 1 by k plus 1 root, then the image between them will be pi by k plus 1 if they are having angle is pi. So you consider the line meet gamma 1 and gamma 2 meet at x naught. So they are having an angle pi by pi here. So its image will have angle pi by k plus 1 with k greater than 1. But remember that these images are subarcs of unit circle. So this cannot happen. They cannot have angle pi by k plus 1 with k greater than 1. So this contradiction leads to the fact that f dash x is not equal to 0. So hence we proved that f dash f is 1 1, and we could extend this Riemann map to the boundary, provided the boundary satisfies certain property. In fact, you can actually extend to the any kind of gamma which has either two-sided arc, or the only condition which we require is that it should be a free boundary arc.